AS Maths Statistics Chapter 4 Correlation Section 4.1. In statistics, there's a certain type of data that we sometimes study which has two variables, and the name for that type of data is bivariate data. Bi meaning two, variate variables, so two variables. It is often represented using think about this, two variables. You probably saw these at GCSE. It's a scatter diagram where each value of one of the variables is paired with the value of the other variable, and one on each axis. The independent, or sometimes called the explanatory variable, is the one that can be controlled. It's very important that you know this. You could be asked to identify which is the independent variable, or you could be asked which is the explanatory variable. So it's always the one that the person doing the experiment can control. The other one is called the dependent or the response variable, and that's y. That one is measured. So one is controlled, the other is measured. So make sure you know the difference. Identify the variable that we can control and choose its values. That's the independent one. It goes on the x-axis. The other one, which responds to the x values, or the one we are measuring, that is the one that goes on the y-axis. Now next up, we're going to look at a few scatter diagrams. The word correlation means, or it describes, the linear relationship between the two variables. So if there is a straight line relationship, so on a scatter graph you'd see the points fitting close to a straight line, then it has linear correlation. This type of a correlation that we study at A level cannot describe any non-linear relationship. So there's a link here with pure maths. Sometimes in pure maths we look at data that fits an exponential model. Population growth is often an example of that. Over time, the population of a country, or just the number of people on the earth, grows exponentially. The rate at which it grows increases with time. So this type of correlation that we're studying here in statistics can't work unless we have a straight line relationship. 5 little diagrams here representing strong negative correlation first of all, and then weak negative correlation on the second one. On the second one you can see that the points are quite close to a straight line, but they're a bit more spread out than the previous one. So the correlation is stronger on the left than it is on the one on the right. If we look at the one in the middle, you'd struggle to put a line of best fit on there. It could be really pointing in absolutely any direction. So we'd say there's no correlation, or no linear correlation at all. And then we've got two more examples. Weak positive. Yep, there seems to be an increasing trend here. So positive means both variables are increasing at the same time, whereas with negative correlation, as one variable increases, the other one decreases, or vice versa. And the final example, again, positive correlation, but stronger than the previous one. The points are closer to a straight line. As I just said a moment ago, you need to know that positive correlation means as one variable increases, the other one also increases. And then negative correlation means as one variable increases, the other one decreases. Next up, two variables have a causal relationship. Please don't misread that as a casual relationship. Definitely a causal relationship. If a change in one variable causes a change in the other variable. And very importantly, we use our judgment to determine this. Which leads us to a very, very important point from the world of statistics, and that is that correlation does not imply causation. What that means is if two variables seem to have correlation on a graph, that doesn't mean that they are affecting each other. So if two things correlate, this does not necessarily mean that one causes the other. Correlations between two things can be caused by a third factor that affects both of them. It's also possible that we're going to see graphs where it looks like there's some correlation, but when we use our judgment and our common sense, we know it's just happening by chance. There's a fantastic website, and here it is, called Spurious Correlations. It's on a website called tylervigan.com. If you just Google spurious correlations, this will take you here. He's also turned it into a book as well. So what he's done is trolled loads of data, simply looking for instances where two data seem to correlate, but using our common sense, we know that it's happened just by chance. So this first example here is graphed US spending on science, space and technology. And then that seems to correlate with suicides by hanging, strangulation and suffocation. Yeah, that data, it does look like there's correlation here. Yeah. This is clearly just a case of happening by chance. Or there could be some third or fourth factor into play. But given enough data, and there's billions and billions of data around nowadays, you're always going to find examples like this. Here's another one. The number of people who drowned by falling into a pool correlates with the number of films Nicolas Cage appeared in. So in the years when Nicolas Cage only did one film, the number of people drowning by falling into a pool was a bit lower than it had been in previous years. But then in a year when he did 4 films, the number of people drowning by falling into a pool was also higher than normal. And again, our common sense tells us these two things are not causing each other. There's no causal relationship here. Let's just have a look at another one. Per capita cheese consumption correlates with the number of people who died by becoming entangled in their bed sheets. Is this just happening by chance, this data, or is there actually a causal link? We've also got divorce rate in Maine, which I believe is in the United States, and then correlates with per capita consumption of margarine. So people are eating less margarine, and the divorce rate seems to be going down at about the same rate. It's a great, really interesting website, tylervigan.com, or just search on a search engine for spurious correlations. There's loads of examples, and also this turn it into an ebook as well. So the point I'm trying to make there is that if two variables correlate, it does not prove that one is causing the other. It's a mistake often made in the real world. Make sure you don't make that mistake.